Lesson 2, Graphing. To sketch the graph of a rational function, we're going to determine and then use the non-permissible values of x, so deciding whether they're wholes or vertical asymptotes, the equation of the horizontal or oblique asymptotes, the behavior of the graph near those asymptotes, and the intercepts. So example 1, sketch the graph of this rational function, then state the domain and the range. So the very first thing that we want to do is we want to factor the numerator and the denominator. I'm going to factor out a negative out of the denominator so that it becomes x minus 4. In the numerator, I can factor that into x minus 4 and x plus 3. So we end up with a factor in the numerator and denominator that cancel out. So part 1 was to look at non-permissible values. Our first non-permissible value is that x cannot equal positive 4. Because this is a common factor in the top and the bottom, means that we will have a hole in our graph at x equals 4. And we can find out what the y value is by substituting in 4 into our new equation. This equation, when we simplify it, actually becomes y equals, I can bring the negative up from the bottom, and so we have negative x plus 3. If I substitute in positive 4, I have y equals negative 4 plus 3. 4 plus 3 is 7, so I have y equals negative 7. So I'm going to have a hole in my graph at the point positive 4 and negative 7. So this point is going to be a hole in my graph. Okay, I end up with no vertical asymptotes for this one because I have no other values that are non-permissible. I can look at intercepts then. Because my denominator actually disappears, the graph of my rational function is actually going to look like the graph of y equals negative x plus 3. I can do some simplifying here and say that y equals negative x minus 3, right, if we distribute that negative sign in. So we're looking for intercepts. From that, I know that my y-intercept is at y equals negative 3, because this is in y equals mx plus b. To find the x-intercepts, I'm going to substitute in 0 for y, so I have 0 equals negative x minus 3, or x equals negative 3. So looking at my graph, I have x equals negative 3 is my x-intercept. Y equals negative 3 is my y-intercept. This is now a straight line. So the graph of my rational function looks like that straight line, except for it has that open circle. And so using a ruler to connect, I end up with a nice straight line for my graph. This is the graph of the rational function y equals x squared minus x minus 12 over 4 minus x. To state the domain and the range, the domain would be x such that x is an element of real numbers. However, x cannot equal positive 4. The range, our range again is all real numbers except y cannot equal this undefined or this open circle here. Our y value was negative 7. Example number 2, y equals x squared over x squared plus 2x minus 8. So again, let's start by factoring. Our denominator will factor into x plus 4 and x minus 2. There's no common factors in the top and bottom, so that means that I will have vertical asymptotes at x equals -4 and x equals +2. So on my graph, a vertical asymptote means that I'm drawing a dashed line at -4 and another one at +2. I can look at horizontal asymptotes. Horizontal asymptotes, we need to look at the degree of the numerator and the denominator. Because the degree is equal, I need to look at the leading coefficients in the numerator and the denominator. Leading coefficients are 1 over 1, so I have a horizontal asymptote then at y equals +1. Remember that with horizontal asymptotes, it just means that our graph approaches that value, but it may actually cross. The next step is to look at the behavior near those points. Looking at our behavior near the asymptote, our first asymptote is at x equals -4. So we want to look at what happens as x approaches -4. And we're going to start from approaching -4 from the negative side. If we look at that, our equation of our rational function, I'm just going to rewrite it over here, is y equals x squared over x plus 4, x minus 2. So what happens as x approaches -4 from the negative side? So if we put in something like -4.1. If I put in -4.1 into the numerator, I would end up with a positive value. Into the denominator, if I put in -4.1, that first term would be negative, as would be the second term. And overall, our function would be positive. So as x approaches that asymptote from the negative side, y would approach positive infinity. On our graph, what that means is this is our asymptote at -4. So as x gets close to -4 from the negative side or from the left-hand side, y is going to get bigger and bigger. And so we can put a little branch of our graph up there. We don't want to make that branch very big because we don't know what happens as x goes towards the left. So we're now going to approach that asymptote. We've looked at it coming from the left. I now want to approach it from the positive side or from the right. So as x approaches -4 from the right or from the positive side, we want to look at what happens to y. So again, let's pick a number that is close to -4, but on the right-hand side, so something like -3.5. Well, again, in the numerator, -3.5 squared is a positive value. -3.5 plus 4 would be positive. -3.5 and -2 would be negative. And so what happens is that as x approaches -4 from the positive side, y will approach negative infinity. So as we come from the right-hand side, our function is going to approach negative infinities. And so we have our second branch. Now we can look at this next asymptote and look at what happens as we get close to it from a negative side. So as x approaches +2 from the negative side, what happens to y? So picking a value that's close to +2, so maybe 1.9, the numerator would be positive. The denominator, 1.9 plus 4, is positive. 1.9 minus 2 will be negative, and so y will approach negative infinity. So as we approach this asymptote from the left, we are going to approach negative infinity. We just have one place left to look at for vertical asymptotes, and that's approaching positive 2 from the right-hand side, or from the positive side. So as x approaches 2 from the positive side, we want to see what happens to y. If we pick a value like 2.1, our denominator will be positive. 2.1 plus 4 is positive. 2.1 minus 2 is positive. So y is going to approach positive infinity. So back up on our graph. As we come close to this asymptote, our y values are going to get bigger and bigger. So we have now 4 branches to look at, or that we know the position of for our vertical asymptotes. The next step is to look at what happens as our values approach that horizontal asymptote. Our function could actually cross that horizontal asymptote and just get closer and closer to it. So what could happen is our function can come towards this horizontal asymptote. It could actually cross it and then come back up. So it could look something like that. Or, let's get rid of that. It could just come down and get closer and closer to that asymptote without ever crossing it. So we need to be able to determine which one of those things happen. So to do that, if it crosses that asymptote, then if I substitute in, this is y equals positive 1. So if I substitute in positive 1, I should be able to find the point where it crosses, if it does indeed cross. So we're going to test at our horizontal asymptote. So our horizontal asymptote is positive 1. So I have positive 1 equals x squared over, and I'm going to use the non-factored form of the bottom. So the non-factored form of the bottom is x squared plus 2x minus 8. If I cross multiply, I end up with x squared plus 2x minus 8 equals x squared. Our x squareds will cancel out, and I have 2x minus 8 equals 0. So 2x equals 8, or x equals 4. Because we actually can get a solution here, that means that our graph is actually going to cross that horizontal asymptote at x equals 4. So at x equals positive 4, we are actually going to have a point on our horizontal asymptote. So let's look at what happens. That is the only solution that we found. So as we move, if we start with this branch here, as x gets bigger and bigger, we know that it has to cross that horizontal asymptote. But because that is a horizontal asymptote, we know that it is eventually going to come back and just approach it. We don't know how far down that bump is, but we're not going to worry about it at this point. Because we had no other solutions when we tested that horizontal asymptote, I know that as x gets very large and negative, my graph is going to come down and approach that value of y equals 1, but it will not cross. Leaves us the 2 middle branches. In order to connect those 2 branches, if it cannot cross that horizontal asymptote, it's just going to come up close to it and then come back down. Actually, let's back that up a little bit. If it does that, I should actually be able to find my x-intercepts. So let's look at finding intercepts first. Okay, so intercepts. So we're going to let x equal 0. If I let x equal 0 in my equation, I end up with y equals 0 squared. Excuse me. 0 squared y squared equals 0 squared over 0 squared plus 2 times 0 minus 8. Well, because my numerator is 0, I end up with y just being equal to 0. So my intercepts then are at the point 0 and 0. What that means on my graph, 0, 0 is the only x and y intercept, so it's going to come up, touch that point, and then come back down. Okay, our next example. Again, we want to start by factoring. So if we factor our numerator, we end up with x plus 4 and 2x minus 3. In the bottom, we have x plus 2. So we don't have anything that crosses off, so we have no holes in our graph, which means that we will have a vertical asymptote at x equals negative 2. So let's draw that in right now. X equals negative 2. Here's my vertical asymptote. Horizontal asymptotes. I need to look at the degree. Because the degree of the numerator is greater than the degree of the denominator, I'm actually going to have an oblique or slanted asymptote. To find the equation of that oblique asymptote, we're going to use synthetic division. So 2, 5, and negative 12. On the outside, we're putting positive 2. Completing the synthetic division, we end up with 2. 2 times 2 is 4. Subtract is 1. 2 times 1 is 2. Subtract is negative 14. This is my remainder. Tells me that the equation of that oblique asymptote is y equals 2x plus 1. So I could draw that in because I know that my y-intercept of that oblique asymptote is positive 1. It has a slope up 2 over 1. And so we're going to end up with that oblique asymptote being this straight line that goes this way. Okay, we want to test the behavior near those. So let's start with that vertical asymptote. I want to see what happens as x approaches that vertical asymptote from the negative side. So as x approaches, that vertical asymptote is at negative 2. From the negative side, what happens? When we substitute it into the numerator, if we look at our factored form, that factored form of our rational function was x plus 4 times 2x minus 3 all over x plus 2. So picking a value that's close to negative 2 but on the negative side, so I could have negative 2.1. If I do that, negative 2.1 plus 4 will be positive. Negative 2.1 times 2, subtract 3 will actually be negative. And in the denominator, negative 2.1 plus 2 will be negative. So overall, my function will be positive, so y will approach positive infinity. So back up on my graph, as I approach this vertical asymptote from the negative side, my y is going to be approaching positive infinity. So it's going to be going up like that. Let's look at what happens as we approach it from a positive side. So as x approaches negative 2 from the positive side, what happens to y? So I put in something like negative 1. I end up with a positive on the top. Negative 1 times negative 2 will give me negative. And on the bottom, negative 1 plus 2 will be positive, so I end up with a negative value, so y will approach negative infinity. So as I approach that asymptote from a positive direction, y is going to approach negative infinity. Now we can test to see whether our graph actually crosses our oblique asymptote or not. To do that, we need to substitute into our equation. So our equation is y equals 2x squared plus 5x minus 12 all over x plus 2. And we want to substitute in here the equation of our oblique asymptote. So our oblique asymptote is 2x plus 1. So substituting that in. I need to cross multiply. When we cross multiply, we need to distribute, and we end up with 3x squared plus 5x plus 2 equals 2x squared plus 5x minus 12. Our 5x's will cancel out. When I subtract 2x, I end up with x squared equals, if I subtract 2, negative 14. Can't take the square root of a negative number, so that means that this equation is undefined, or there's no solutions. This means that our graph does not cross that oblique asymptote. So if we look at what happens, it means that it needs to approach, as x gets really big, it needs to approach that oblique asymptote. So it's going to be something like that. As it approaches our oblique asymptote, it'll come up like this. We can go back and find our intercepts to give us a little bit more accuracy. So if we let x equal 0, we end up with y being equal to 2 times 0 squared plus 5 times 0 minus 12 all over 0 plus 2. Well, all of these are 0, so negative 12 plus 2 means that we cross at y equals negative 6. So I should have crossed here, so I'm going to have to back my graph up a bit. It's the danger of making those branches too long. So my graph is going to cross here. Let's check for x-intercepts. X-intercepts, we're going to let y equal 0. When we let y equal 0, we have 0 equals, and if I use the factored form this time of my numerator, I have x plus 4 and 2x minus 3. Means that I will have an x-intercept at negative 4 and another one at positive 3 over 2, sorry, so positive 1/2. So x equals negative 4. My graph should have crossed here. Again, I apologize. I should have found those x-intercepts first. And at positive 1.5, so it's going to go through there. My curves are not very smooth, but that's roughly what it would look like. Last example. Y equals 2x plus 3 over 2x squared plus 9x plus 9. Again, we want to start by factoring. The numerator is already factored. The denominator will actually factor into 2x plus 3 and x plus 3. I have a common factor, which means I will have a hole in my graph. The hole will be located at x equals negative 3 over 2. I will have a vertical asymptote at x equals negative 3. So let's draw in that vertical asymptote. So x equals negative 3. My vertical asymptote is here. I can figure out the y value of that hole by substituting in negative 3 over 2 into my simplified equation. So this equation, when I simplify it, actually becomes 1 over x plus 3. Substituting in negative 3 over 2, I end up with y equals 1 over negative 3 over 2 plus 3, which will simplify into 2/3. So at negative 3 over 2, I have a y value of negative 2/3, or sorry, positive 2/3, so I'm going to have a hole in my graph. I'm going to make that a little bit bigger just so it actually shows up as a hole. There we go. Okay, next step. I can look for horizontal asymptotes. If I look at horizontal asymptotes, the degree of the numerator is smaller than the degree of the denominator. So that means that my horizontal asymptote is going to be at y equals 0. So it's going to be that positive, or sorry, right along the x-axis. Looking at end behavior, let's approach that vertical asymptote from the negative side. So as x approaches -3 from the negative side, I end up with, my equation has simplified into y equals 1 over x plus 3. So if I put in a value such as -3.1, the top is equal to 1. The numerator, -3.1 plus 3, will be a negative value. So as x approaches -3 from the negative side, y is going to approach -infinity. So we're going to be going down here. I'm going to be careful not to make those branches too big this time. As x approaches -3 from the positive side, we end up with 1 over, as we get really close to -3, so we could use -2.9, we will end up with 1 over a positive, so y will approach positive infinity. So that branch is going to be going upwards like that. To test to see whether it crosses our horizontal asymptote, we're going to substitute our horizontal asymptote, which is y equals 0, into our equation. So we have 0 equals 1 over x plus 3, which when we cross multiply, the x's will disappear. We get 0 equals 1, which is no solution, so therefore it does not cross. That means that as x gets very large and positive, it's going to approach our asymptote. As x gets very large and negative, our value is going to also approach that asymptote, but it will stay on the negative side. Okay, I'm not going to have any x-intercepts since the asymptote actually falls on the x-axis, so I can connect this side of my graph this time. I'm not going to connect to the other side yet because I want to look and see where my y-intercept would be. So to find my y-intercept, I'm going to let x equal 0. If I let x equal 0, I have y equals 1 over 0 plus 3. So y will equal 1/3. So that's my y-intercept. So it's going to be right in here. Again, difficult to do on the smartboard. Now that I have those intercepts, now I can correct my graph. So it's going to approach, not quite go through that point. We're going to have an open circle there, and then approach that asymptote.